Hi, welcome back. So, the goal of these couple of videos now, I'm going to do some problems from the end of chapter that I already assigned for you from the homework. So, I want to go over some of them just for practice. So, I would say do the homework first, attempt those problems, and then look at my solution that I will do here on the board, as well as the solution that the book posts that I have also included in the homework solution. And so only consult these if you're stuck. And then if you do it correctly, make sure you just watch it just to see if I did it differently. Or maybe you found a clever way of doing it, a better way. Um, and if you get stuck and you watch this one, then make sure that you do it again with a fresh mind in a day or two when maybe you don't remember the solution as vividly and just attempt it. And so you will gain problem solving skills, right? So the governing principle here that we're going to do is basically Newton's law. And when I say Newton's law, I mean Newton's three laws. Mainly it's the second law, F equal to ma. So we need to first figure out, make sure we have a coordinate system for every, if we have two connected bodies, then, or three, we have a coordinate system for each of them. Or maybe one coordinate system for all, it doesn't matter. It's your choice. And then find all the forces on each object, and then set that net force to equal to the mass times acceleration. Also make sure you read the problem, because sometimes they will tell you that the objects are not accelerating. So in that case, then the acceleration is equal to 0. So make sure you completely read the problem. So let us look at the problem here, the first one. You have two objects that are connected. So let me go to the board. I will use this one. Yeah. So you have two objects that are connected. This is a 2 kilogram mass. This is a 1 kilogram mass. And apparently they're made of different materials, because this one experiences a friction of only 0.1, and this one experiences a friction of 0.2. Notice this one has higher friction than this one because they want this one to lead, because this one experiences lesser friction, so it wants to go down faster than this one. So if you cut the string, they're not connected, this one will lead. It will go down farther, much quicker than this one, because this one experiences a higher friction. But they're connected, so this one can't get farther than the length of the string ahead of this one. So this one is always leading, so the string is always has tension, because this one is kind of dragging it. And the question is, what is the acceleration? And then what is the tension in the string? So as usual, you look at this problem here, and they would accelerate downhill. There is no acceleration perpendicular to the plane, and so the convenient way to draw the axes is this way. This is the x direction along the plane, along the incline, and the y direction is perpendicular to it. And so let us look at the 2 kilogram first. So here is the 2 kilograms. What are the 2 kilograms? 2 kilograms. What are the forces on it? Well, there is mg straight down, mg. And then there is the normal force. Let me call it, since this one is the first mass, I'll call it normal force 1. And then they're telling me that there is friction, and so friction opposes the motions. If it's sliding down the incline, then the friction will be up the incline. So there is the force of kinetic friction, and I would call it force of kinetic friction 1. And the question is that it? Well, let's figure out. There is mg because we're on Earth. There is a normal force because it's in contact with the plane. There is frictional force due to the surface, due to the plane itself, and because there is coefficient of friction. Is that it? No. It's connected here by a string, and so the string would give you tension. I'll just have tension. Is that it? The answer is yes. That's it. So we have to include everything, but don't make up anything that doesn't exist. Notice the mg, our axes are parallel and perpendicular to the plane. Mg is in this direction that is not parallel, that's not perpendicular, so we have to break mg into a perpendicular component. This one is the mg cosine of theta, and a parallel to the plane component. That's the one that causes the acceleration. It's the mg sine of theta. And by the way, this is mass 1, so I'll call it m1, 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 and it's 2 kilograms. I'll substitute the numbers. So let's apply Newton's second law to this mass. Newton's second law, remember, can't emphasize this enough. The net force on an object is equal to that object's mass times its own acceleration. The object at hand here is the 2 kilograms that we're talking about. What are the forces on it, on the 2 kilograms? Don't worry about the 1 kilogram yet. We'll worry about it in a moment. So it turns out that we will have 2 unknowns, and that's why you need this object to figure out the second unknown. You need 2 equations to solve for 2 unknowns. So we'll say our 2 kilogram object does not move in the y direction, so the acceleration in the y direction is 0, so the net force in the y direction is 0. In the y direction I have n1 and m1g cosine theta in the negative y direction, and so n1 has to equal to m1g cosine theta. So I get that n1 is equal to m1g times the cosine of theta, and therefore the force of friction, F kinetic friction 1, will equal to m1g, the force of friction is the coefficient of friction times the normal force, so it would be mu k, and it's mu k 1 because we have 2 different mu k's here, so mu k 1 times the normal force, which is m1g cosine theta. Let me just figure out what this number is, fk1. Let's just figure it out. So we'll have 0.1 times 2 times 9.8 times the cosine of 20 degrees. So let's do that. Let's just do it. So 0.1 times m1, which is 2 kilograms, times 9.8 times the cosine of 20 degrees. Hopefully 1.84, I don't make any mistakes. 1.842, let me quickly, 1.842 newtons. If I make a mistake, I have to come back to it, all right? I'm doing these fresh. Again, the rationale is you see me struggle through the problems, through reading them and plugging in the numbers, and I think that's healthy. Okay, so that's that. Great. So now we applied Newton's second law in the y direction for m2, for the 2 kilograms, and that gave us the normal force and it gave us the force of friction. Now we will apply Newton's second law in the x direction. In the x direction, this is the positive x direction, so I have 3 forces in the x direction. I have the component of mg down the incline, and I'm calling that the positive direction. So I have m1g sine theta. I have the tension up the incline, but that's the negative direction, and I have the force of friction up the incline also, and that's the negative direction. So let's see. So the net force on object 1 in the y direction will equal to the mass of object 1 times the acceleration of object 1. And I will not call it A1 because object 1 and object 2, they're connected. They will have the same acceleration. So I have m1g sine theta, that's down the incline, so I have m1g sine theta, and then minus the tension, or minus fk1, and then minus the tension, equal to m1 times the acceleration. And so I think we should probably substitute also in this problem. I don't think it's worth keeping everything in symbols. So I have m1g sine theta. Let's figure what that is. M1 is 2 kilograms times g, which is 9.8, times the sine of 20, plus, or actually minus fk1, so minus fk1, which is 1.842. And so that gives me That will give me 4.862, 4.862 minus the tension equals to 2m. The m1 is 2, so 2 times the acceleration, twice a. So I have this, basically. And I have two unknowns there, the tension and the acceleration. So I want to now move on to this one. Very similar logic. I will use the x and y direction. What are the forces on the 2 kilogram? I'm sorry, on the 1 kilogram. Let's do some. In fact, let me do the work on here on this board on this side. Here's the 1 kilogram. Here's the 1 kilogram. The 1 kilogram. And kilogram. So what happens to the 1 kilogram? Well, 1 kilogram has a force mg downward. I will call it m2g because it's the second mass, m2g. It's in contact with the plane, so there is the normal force. Let me call it n2. What else? There is a string it's connected to a mass here. Strings only pull, so there is tension. Notice the tension is down the incline for this one because the string always pulls, so it pulls this mass upward and it pulls this mass downward. It slows this mass down from going as fast as it wants to do, and it speeds up this one because it has higher friction. Now, is that it? No, there is force of friction, and the force of friction is opposing the motion. The motion is down, so the force of friction is upward, and let's call it Fk2. So, let me keep doing the side work here. So we get here the normal force 2. Similar to the logic here, normal force 2 will equal to m2g cosine theta. Equal to m2g cosine theta. And therefore the force of friction 2 will equal to mu k2 times m2g cosine theta. And so that gives the force of friction 2 will give us what? Well, we need to plug the numbers in. Mu k2 is, this is mu k2, not mu k squared. Just mu k, I'm labeling it as 2 for mass 2. So it's 0.2 times m2 is 1 kilogram times 9.8 times the cosine of 20 degrees. That gives me 1.842. 1.842 newtons. That's the force of friction. And now we will use Newton's second law for this mass here in the x direction. So let me keep writing with a different color. Yeah, the net force in the. So I made a mistake here. It should say the net force in the x direction. It should say x direction. So the net force in the x direction on mass 2 will equal to mass 2 times the acceleration. What are the forces on mass 2 in the x direction? You got the tension downward. Is that the positive direction? Yes, because we chose this to be the positive direction for both of them. So be the tension. Okay, what else? Is that it? No, the answer is no. You see, M2G has two components. One of them is perpendicular and one of them is parallel. So there is this component of the M2G. So there is M2G sine theta. So there is tension positive, M2G sine theta also positive. So plus M2G. What am I doing? I should be here. Plus M2G sine theta. And then there is friction up the incline minus Fk2. Those are all the forces in the x direction, and they have to equal to the mass times acceleration, m2 times the acceleration. I still don't know the tension, so I have here, so I get tension plus. Now I have to plug in the numbers for this one and subtract FK2, which is 1.84. So let me do that in one step. M2 is 1 kilogram times G is 9.8 times the sine of 20 degrees. So this is 3.352 basically, minus the force of friction, minus 1.842, so minus 1.842. I get 1.51. 1.51 equal to MA. M1 is, M2 is 1 kilogram, so 1 times A, that's just A. So I have this. Now I have my two equations, two unknowns. What do I do with them? Well, I have to solve them. The easiest way to solve them is, I see a minus t here and a positive t here, add them, add the two equations. So when you add them, the t disappears, and you just have the 4.866 plus 1.51. So I get 4.866 plus 1.51, let's do it. 4.866 plus 1.51, that gives me 6.376, so I get 6.376 by adding the two equations. The t disappears, so that's it on the left hand side. On the right hand side I have twice a plus 1a is 3a. Let's hope after all this work I get the numerical value for the acceleration to be correct. Hopefully I didn't make any mistakes. That's always a problem. And then I will check the solution. Divided by 3. So get the acceleration to be 2.125. 2.125 meters per second squared. Let me just check my solution here. Give me a moment. So the solution says 2.12 meters per second squared. Yeah, so we're good. So that's the acceleration. And now let me check, well, we need to calculate the tension. Well, we have options now to calculate the tension. You can go to this equation and calculate the tension, or go to this equation and calculate it. I think this is simpler. So the tension, I can write tension, this is for part B. The tension will just be the acceleration, whatever it is, minus 1.51. And so I have 2.125 minus 1.51. And so the tension will be minus 1.51, 0.615, about 0.62 newtons. And let me also double check that number. Yeah, they have 0.61. They probably rounded. We didn't round much. Okay, so whatever it is, that is the case. The important part is the process of the problem solving. Okay, so now let me go to the next example here, which I wrote ahead of time. Let's read it together. So it says a 4 kilogram box is on a frictionless 35-degree slope and is connected via a massless string over a massless frictionless pulley. So everything is frictionless here and ideal. Okay. And then it's connected to a 2 kilogram object as shown. And then it says, what is the tension in the string if the 4 kilogram box is held in place so that it cannot move? And then if the box is released, which way will it move in the slope? And then it says, what is the tension in the string once the box begins to move? Okay. So let's look at the first one here. This one is kind of conceptual. So you have a 4 kilogram here, a 2 kilogram here, no friction. The angle is 35 degrees. So at first it says, what is the tension in the string if the 4 kilogram is held in place so it cannot move? This is an ideal tension, ideal pulley, so the tension throughout will be the same. So imagine you put your finger here, or just grab the 4 kilogram and not make it move. So what happens? Nothing is moving. It means the net force is 0. If the net force is 0, the acceleration is 0. If the acceleration is 0, it's 0 for both boxes. So it's probably easiest to look at this one. So I'm holding this one. This box is not moving. And the tension is the same throughout. So here's this box. Let's look at the 2 kilogram by itself for part A. What are the forces on the 2 kilogram? Well, there is the earth pulling it down with mg. m2g. Let's call this one 1 and this one 2. m2g, and then there is the tension upward. And they have to add up to 0. They have to add up to 0. That's the net force in this, let's call it the y direction. The net force is equal to 0. So the tension minus m2g equal to 0. That means the tension is equal to m2g. And so the tension is equal to, it's m2g. So it's 2 kilograms times 9.8. So that's 19.6. So I get tension is 19.6 newtons. All right. So that's that part. So we did the first part rather quickly. Let's look at the next part, which is the more interesting. So now you let go, and the two boxes will start to accelerate in a certain way. They either do this, or they either do that, right? Or maybe they even balance. They might even balance. So how do we know whether they move, whether this mass moves down and this one moves up the incline, or whether this mass moves up the incline and this, moves up and this one moves down the incline? Or maybe they don't move. How do I figure that out? Well, let's assume the motion to be in a certain way. I would just assume this mass falls and this one rises. And then calculate the acceleration. If I get a positive value for the acceleration, it means my assumption is correct. If I get a value for the acceleration that's negative, it means my assumption was wrong and the acceleration is actually in the opposite direction to what I have assumed. If I get 0, then the acceleration is 0. So let's do that. So let's look at the 2 kilogram box by itself. Let's look at it. Here's the 2 kilograms. We're going to draw a coordinate system for the 2 kilograms on its own. And I'm going to call it M2. I chose to call it M2. There is tension. There is M2g, and I'm assuming it's accelerating this way. And the acceleration for both boxes would be the same in magnitude. And I'm going to take this to be the positive y direction as a choice. It's up to you. It's up to us. Okay? I can choose downward to be the positive y direction, to be along the acceleration. It doesn't matter. Okay. So let's see. So I chose that upward to be positive. So the net force on M2 will equal to M2 times the acceleration. Notice M2 doesn't have an x direction. It just moves along one direction. So I get the net force on it is the tension minus M2 times g equal to M2 times the acceleration. I made one mistake. I'm assuming downward to be negative, so I better put a minus sign here. A minus. So I get the fact that the tension, right? I'm assuming it's accelerating downward, and so the acceleration would be like this, as a vector, if you like. It would be minus some number here times j hat. That's the negative y direction. That's what I'm doing. But since it's the y direction, everything has a j hat, you might as well just drop that j hat. And so the acceleration is just negative a. I'm assuming it's down. All right, so the tension would be m2 times g minus m2 times a. That's the tension. Let's look at this box now, and let's draw something for it. Here it is. So what are the forces on it? Well, it's connected by tension, so there is tension this way, and it's the same tension because it's an ideal string. There is a normal force because it's in contact with the plane. There is normal force. There is gravity because it's on Earth, so you get M2, or M1 actually, M1G. There is no friction, so that part is fine. And I ask, is there anything else? The answer is no. And so that's it. Now gravity will have two components. You got M1G cosine theta, and you got M1G sine theta. How am I going to choose my coordinates? I'll choose It's up to us. I can choose this to be the positive x, and this is the positive y direction. There is no motion in the y direction. There is no friction, so I don't really care about the normal force. If there is friction, then we will say the normal force is equal to m1 g cosine theta, and friction would be the coefficient of friction times the normal force. There is no friction, so I don't care about it. Don't worry about the y direction. So we'll say here's the x direction. We're assuming this mass falls, so this mass rises. So the acceleration is positive for this one because it's up the incline by assumption. So I would say, all right, the net force in the x direction for m1 will equal to m1 times the acceleration, and the acceleration in the x direction for m1 is positive. So that's fine, because it's up the incline. What are the forces on m1? Well, you got the tension upward, up the incline, and then you have, actually let me go in one line. So you got the tension up the incline minus m1 g sine theta down the incline. That's it, those are the only two forces in the x direction, equal to m1 times the acceleration. So we get the tension would equal to m1 g sine theta plus m1 times a. So these two have to equal to each other, because t is equal to this and t is equal to that, so they have to be equal. So I'm going to combine these two equations and set them equal to each other. So I get, let's combine them, let's write with a different color. So I get m2 g minus m2 a is equal to m1 g sine theta plus m1 times a. I have that. So I'm going to move this to the other side, so to collect the acceleration, and then move this one to this side. So I would have m2 g minus m1 g sine theta will equal to, move this one to the other side and factor a, so you get m1 plus m2 times the acceleration. And then, oh, I could factor a g out of here, so let's do that. Put a g here, just factor it. So you get the acceleration will equal to m2 minus m1 sine theta. I'll put the g in front, this g I'll put it in front, divided by m1 plus m2. Okay, so I have a formula for the acceleration. So if m2 happens to be larger than m1 times sine theta, my acceleration will be positive and it will go the way I assumed. If m1 is not heavy enough, or if m2 is not heavy enough, or m1 is large enough, or theta is also steep enough, you might have a negative value for the acceleration, in which case it will, instead of going like this, it will go like that. And if m2 happens to exactly equal to m1 sine theta, then you get a 0, and the acceleration will be 0. And if they are at rest initially, they will just remain at rest. Okay? And so let's calculate the acceleration for our specific values here and see if we get a positive or a negative value. So I get, let's calculate it. M2 is 2 kilograms, M1 is 4. So I have 2 minus 4 times the sine of theta, which is 35 degrees. 35 degrees times g, which is 9.8, divided by m1 plus m2. That's 2 kilograms plus 4 kilograms. So that's a 6 kilogram. 6 kilograms. And we get, let's do that. So I get 2 minus 4 times the sine, not cosine, sine of 35 times 9.8 over 6. So I get 0.48, I'm sorry, negative 0.48. So the acceleration would be negative 0.48 meters per second squared. It's negative. What does it mean? Well, it means it's opposite to what I assumed. I assumed it's going to be, this mass will rise up the incline and this one will drop. It's negative, it means it's actually, this one will rise and this one will drop down the incline. That's what it will be. So the answer here, if the box is released, the 4 kilogram box is released, which way will it move in the slope? So it will move down the slope. It will move down the slope. Because my assumption was it would move up the slope and the acceleration will just, it will have a positive value. But the acceleration is negative. It means it's actually now, I was wrong. My assumption was wrong. That's fine. You can never, I mean, it's hard to guess. I mean, this is 2 kilograms, this is 4. If this were like 8, or if it's even 4, then it would move down. But when the numbers are kind of not so clear, then you just have to take a guess, and if it's negative, then that's fine. You just correct your assumption. So actually, the acceleration is opposite to what I assumed, and this box will move down the incline. And then it says, what is the tension in the string once the box begins to move? Let me make sure I have enough time. And apparently, yeah, let's do that. So we can use any of those. So I get the first one, it says tension is equal to M2 times G minus M2 times A. And so that will be M2 times G minus A. And you plug in the numbers. M2 is 2 kilograms. G is 9.8 minus the acceleration, which is minus 0.48. Notice the minus minus, so it becomes a plus. And the tension will be, let me look it up. The tension will be 21, all right? So make sure you write that down. I'll go to the next clip now, next video.